Welcome to this tutorial on mathematical induction. In this tutorial we're going to look at what induction is, when we can use it, how we can use it, and we'll also cover some examples. Induction is a method of mathematical proof. So in other words, we use it when we want to prove a certain statement is true. And it's a very important technique to understand because it works in a very particular type of situation. And with a bit of practice, you can easily recognize the types of situation where a proof by induction will work. And the chances are that in those situations, a proof by induction will be a lot easier to perform than a proof by any other method. So to start off, suppose we want to prove a certain statement is true for all natural numbers n. So we have a statement which involves a variable n. And this is really the classic type of situation where you would want to try to use a proof by induction. So just as an example, let's try to prove that the sum of the first n natural numbers is given by the formula n times n plus 1 over 2. And this is a very famous formula. You might have seen it before. But this formula doesn't just come from nowhere, it has to be proved. And the easiest way to prove it is by using induction. But before we talk about induction, notice that in this formula, n can be any natural number. So this means we effectively have an infinite number of statements that we have to prove, because we have to show that the statement holds when n equals 1, n equals 2, n equals 3, and so on, going on forever. So we're trying to prove this statement. If you add together the first n natural numbers, the total is equal to n times n plus 1 over 2. Firstly, let's see if the statement is true when n equals 1. Well, when n equals 1, the left-hand side of this equation is just 1, because we're looking at the sum of the first 1 natural numbers, and on the right-hand side we have 1 times 1 plus 1 over 2, which is equal to 2 over 2, which is also equal to 1. So the statement is true when n equals 1. Now if you look at what happens when n equals 2, then on the left-hand side we have 1 plus 2, which is 3, and on the right-hand side we have 2 times 3 over 2, which also gives 3. So the statement holds when n equals 2 also. And then we can look at what happens when n equals 3. And you can show that the statement holds in that case as well. But we can't keep going on like this, because it's going to get us nowhere. Because what we really want to do is prove that the statement holds for all natural numbers n. And since there are infinitely many natural numbers, we would be here forever if we tried to check all of the natural numbers one by one. So obviously we need a different method. So here's the principle of mathematical induction, and we'll look at exactly how this works in a moment. So don't worry if it doesn't make too much sense at first. Basically what it says is that if we have an infinite sequence of propositions or statements, and we call these statements P1, P2, P3 and so on, then we can prove that all of these statements are true by doing two things. First, we prove that the first statement is true, in other words, P1 is true, and second, we prove that if Pk is true, for some fixed number k, then Pk plus 1 is also true. And this will become more clear when we look at some examples very shortly. So when can we use induction? Well, usually, or at least in most of the simple examples that you find in books, etc., you use induction when you're trying to prove that a statement involving n is true for all natural numbers n. So in the example that we've been talking about, we're trying to show that this formula holds for all natural numbers n. And the next question is, how do we use induction? Well, it's really a two-step process, and we rely on the principle of induction that we saw a moment ago. So basically we have a statement which we're trying to prove for all natural numbers n. The first step is to show that the statement holds when n equals 1, and this is called the base step. And the second step is to assume the statement holds when n equals k for some fixed number k, and then use this assumption to show that the statement holds when n equals k plus 1. And this is called the inductive step. And that's all there is to it. So now let's see how this actually works in practice. So going back to our example again, let Pn denote the proposition or statement that we're trying to prove, which is that the sum of the first n natural numbers is equal to n times n plus 1 over 2. And we want to use induction to show this statement holds for all natural numbers n. In step 1, we have to show the statement holds when n equals 1. Well, we already did this earlier. When n equals 1, the left-hand side of this equation up here is just 1, and the right-hand side is also equal to 1. So therefore the statement holds, and we've done the base step. In step 2, we start by assuming that the statement holds when n equals k. So this is not something that we have to prove, we simply assume it's true. And when we make this assumption, we call it the inductive assumption. And this is really the thing that makes induction such a powerful technique, because we can carry on with the proof and use this assumption as if it's a fact. So we assume that the sum of the first k natural numbers is equal to k times k plus 1 over 2. And now we have to use this assumption to show that the statement holds when n equals k plus 1. So in other words, we have to show that the sum of the first k plus 1 natural numbers is equal to k plus 1 times k plus 2 over 2. And basically what we're going to do is use the fact that on the left-hand side of this equation we have the sum of the first k natural numbers, and we've assumed that this is equal to k times k plus 1 over 2. So we've assumed that this equation here is true, and therefore we can write that the sum of the first k plus 1 natural numbers is equal to k times k plus 1 over 2 plus k plus 1, because as you can see, all we've done is use the fact that these two things are assumed to be equal. And now we can take out the k plus 1 as a common factor, since it appears here and here, and so we can rewrite the right-hand side as k plus 1 times k over 2 plus 1, and that's just the same as k plus 1 times k plus 2, all divided by 2. So using a couple of simple algebra steps, we've shown that this is equal to this, and therefore pk plus 1 is true. In other words, the statement holds when n equals k plus 1. And therefore, using the principle of mathematical induction, we can say that our statement Pn is true for all natural numbers n. So let's just reflect on this for a moment and ask ourselves, how can we really be so sure that this statement is true? Because what we're really saying is that our statement holds when n equals 1, it holds when n equals 2, it holds when n equals 3, and so on. So we're saying that we've proved that our statement holds in an infinite number of different cases, and we haven't really done that much work. So how can we say that we've proved this infinite sequence of statements just by doing such a small amount of work? Well, in order to understand this, you have to look at exactly why induction works. So this is what we've done so far. We've shown that our statement holds when n equals 1, and we've also shown that if the statement holds for some fixed number n equals k, then it also holds when n equals k plus 1. So we've shown that if the statement is true for one number, it's true for the next number, to put it in an informal way. But in fact, this is all we need to do, because using these two facts, we can say that since p1 is true, that means p2 must be true, and since p2 is true, that means p3 must be true, and you can keep this argument going on, and say that Pn is true for any natural number n. One of the most popular ways of explaining induction is to use the analogy of dominoes. So you know that if you have a line of dominoes standing up next to each other, and you push the first domino onto the second domino, then that will make the second domino fall, and it will fall onto the third domino, and the third domino will fall, and so on. So eventually all of the dominoes in the line will fall over. So here's the domino analogy for induction. Suppose we push over the first domino in the line, and suppose we also know that when one domino falls, it knocks over the next domino. Then we can be sure that all of the dominoes will fall. So in this analogy, pushing over the first domino is the base step, and proving that one domino knocks over the next domino is the inductive step. So when we try to prove something by induction, it's a bit like trying to knock over an infinite line of dominoes. All we have to do is push the first domino, and then prove that when each domino falls, it knocks over the next domino. And then we can be sure that every domino in the line will eventually fall over.